Hello, we are Team 39 and our topic is learning from sleep data. Sleep quality is important for health as low sleep quality is correlated with various health diseases. Therefore, people nowadays are interested in their sleep quality, especially with the development of various variables that can sense body signals. Sleep quality and sleep stages can be measured by body's electrical activity over time. A polysomnogram or PSG is one of such representation of the measurements. Hypnogram is yet another representation that displays sleep stages over time. And as we can see in the figure on the right, this is a hypnogram. However, the current sleep stage classification or sleep stage scoring is done manually by human experts, which can be very time consuming and expensive. Therefore, in this project, our team aims to develop machine learning and deep learning models that can automatically classify sleep stages from PSG signals. To give a quick overview, we collect raw PSG signaling data from PhysioNet, extract and process the data using MNE library and Apache Spark, especially PySpark. And finally, develop, train, and test the learning models using PyTorch. In data processing, we download PSG data as well as the corresponding hypnogram data from PhysioNet, which includes signals from 197 patients over the whole night. 100 different signals are collected each second. We first extract different channel signals from the PSG data. These one-dimensional channels include 2 EEG channel and 1 EOG channel. We then attach the labels from the corresponding hypnogram to these channel signals. Since not all hypnogram labels are relevant, we remove the unrelated and unknown hypnogram labels as well as the corresponding channel signals. Lastly, we segment the remaining channel data into 30-second epochs. The stages we're interested in classifying include W, N1, N2, N3, and the REM stage.
Our model architecture has three stages. Pre-processing the input data is done in the ETL pipeline. For feature extraction, we use a convolutional neural network architecture, since frequency domain processing for EEG signals has inspired various successful CNNs for this step. Finally, we aim to leverage learned temporal associations with the transformer architecture and self-attention to predict the sleep label. For feature extraction, the convolutional neural network architecture consists of two sections. One has a small filter to capture recent data from the past several sleep epochs, while the other has a large filter to capture long-term frequency trends of various sleep class labels. For sleep stage prediction, we are using a transformers architecture, which was introduced in a natural language setting. The diagram here is showing how the natural language model is trying to infer what the word "it" is referencing to in the sentence by applying self-attention. We leverage this self-attention to identify relevant temporal associations in past sleep epochs to better predict the sleep stage at any given time step. Here is a full view of our model. The base encoder and decoder seen as part A and part B in the diagram are based on the vanilla transformers architecture. The positional encoding component has also been implemented as part C in the diagram. We've added residual layers, which are applied before the model takes the softmax and computes the probability across the 5 possible sleep stages.
These are some quantitative evaluation for our project. We can use several metrics which are commonly used in classification tasks. So the first metric is accuracy, overall accuracy over the test set. The second is the overall F1 score over the test set, and the 5 metrics towards the right are class-wise F1 scores. And mean F1 score is now the mean of these 5 columns. And the methods which we cover is, first is the sleep EEG net, which is a baseline published in 2019. It consists of a CNN plus a bidirectional RNN model to capture the temporal part. The second method is the CNN only part of the method, a part of our model, and the third method is CNN plus transformers, which is our full model. As you can see that we have a lower accuracy compared to the baseline, but we have a higher mean F1 score, and the reason is also evident from this from the class level F1 scores. We perform better on classes which have a lower frequency. These two figures are the loss curve and the accuracy curve for our 20 epoch training. You can see that there is no overfitting, which is a good thing. To conclude the presentation, we were able to build a model which, although doesn't have a higher accuracy than the baseline, it has a better mean F1 score and performs better on the classes which are less frequent. So we think there are several reasons for the good performance. One is that the CNN with two sections to capture recent data and longer temporal duration helps us, and also the transformer model with its self attention is a good model to capture the temporal context, and it also allows us to train faster. And the third, which we think is the most important, is that we use the class balancing in the loss function. So we go over the training set, figure out what's the relative frequency of each class, and use that to weight each term in the loss, and it helped us to perform better on classes which are less frequent. Thank you so much.